Hi, my name is Hope,
My name is Alyssa.
My name is Maria Angela.
and we're doing chapter 17, Aqueous Equilibrium. So the first thing we'll be discussing is buffers. What is a buffer? A buffer resists change in pH by neutralizing added acids or added bases. This can contain either a significant amount of weak acid and its conjugate base, or a significant amount of weak base and its conjugate acid. An example of a buffer would be like in our blood, so that would be H2CO3 or HCO3 minus. An important buffer mixture that's added to blood would be like carbonate or bicarbonate ions. How you can identify something as a good buffer is if you have a significant amount of weak acid and its conjugate base. To make a buffer solution, you will need a significant amount of both a weak acid and your conjugate base. In order, if there's a small amount of NaOH that's less than the amount of acetic acid presented, then the pH change is small. And then if a strong acid is added, it is neutralized by the conjugate base. For example, NaC2H3O2 in a buffer. We also have common ions. So common ions are in a weak acid solution. When you add salt, it contains the anion of Na, and the conjugate base of the acid is known as a common ion, which shifts the position to equilibrium. We also have the Henderson-Hasselbalch equation, which is this equation derives from the Ka expression, which allows us to calculate the buffer solution. So that's pH is equal to pKa plus the log of base over acid. There's multiple ways of deriving it if you have like a formula that's given to you, but generally the main thing would be pH is equal to pKa plus log of base over acid. You'll be given the acid or the base to solve.
Okay, and then to calculate the pH changes in a buffer, there's two parts to it. First, you do the stoichiometry, which is figuring out how any added acid or base reacts with the buffer components, and then the added acid reacts with the conjugate base to make more weak acid, while the added base reacts with the weak acid to make more conjugate base. After that, there's the equilibrium step where you calculate the new pH using the updated concentrations of the acid and base forms. So buffers resist changes in pH because they contain both acid and conjugate base that continuously neutralize the small additions of strong acids or bases. And their effectiveness depends on the relative amounts of the acid and base and their overall concentrations. So you get the ideas of buffer capacity, which is how much acid or base it can absorb before the pH changes noticeably, and the buffer range, which is the pH range where it works best, which is usually when the pH is close to the pKa of the acid. And then for acid-base titrations, a titration is when you gradually add a solution of a known concentration to one of an unknown concentration until they've completely reacted, and that's called the equivalence point. And the titration curve shows how pH changes as the titrant is added. So for a strong acid and strong base, the equivalence point is at pH 7, which is neutral. And then if you titrate a weak acid with a strong base, the curve levels off at above 7 because the solution becomes slightly basic.
And we talked about solubility product constant. We introduced the KSP when we said that it is used to express how soluble an ionic compound is. Each salt has a unique KSP value that quantifies its equilibrium between solid and dissolved ion. We also talked about molar solubility. We define it with S, which is the number of moles of solute that dissolve per liter of solution. We also talked about KSP, and we said that KSP value we can't compare the KSP value directly unless the compound have the same ratio. We also mentioned the effect on common ion. We said that it decreased the solubility of the compound. For this chapter, what helped me for this chapter was the homework and also some video about this chapter and also some practice question. That's what helps me about this chapter. Thank you.
Thank you.
Thank you.
Yeah.